Hello, hello. How are you all doing?
Good, how are you?
Hanging in there, you know. My husband and I took our 4-year-old daughter and our 5-month-old baby camping this weekend. And it totally worked out and it was so fun.
Oh, that's awesome. I'm glad you guys were able to get away for a little bit.
Yeah, it was great. It was great. We were a little scared, but about how we were going to deal with an infant out in the woods, but it worked out just fine. So hopefully everybody else got out and got to enjoy some of that good weather. I love fall in Asheville. It's amazing. It's a real fall. If anyone's from like up north where I'm from, there is no such thing as fall. It's like summer and then winter and then summer again. So it's really, really great to see all the leaves starting to change.
I had to finally flip my closet. So like all of my coats are now in the front of the closet and all the shorts and stuff are in the back.
Oh, and I love it. And I love like wearing sweaters and like wearing comfy, cozy socks. It's just very, very pleasing for me at least. Until it's not, and then I'm ready for summer again. And then in Asheville, it's great because the seasons are actually, 3-4 months. So then it's time for it to get warm again when you're over it. Okay, so we are going to get started on, we finished up isotopes last time. We finished up all the atoms and element stuff. So we're going to get started on compounds and molecules. So this chapter is, hopefully now we've got our building blocks, right? We know where the elements are on the periodic chart. We know how to find the information on them. And now we're going to start putting them together into compounds. In addition to writing formulas and things like that, we're going to work on nomenclature in this chapter, which is just a fancy way of saying naming, which is always really important in chemistry. You guys get to do 2 types of naming. You get to name your inorganic stuff, and then later on in the semester, we're going to get to name organic stuff as well. But naming is just really, really important because if you don't know how to name a compound, you're going to look at these things and say, I have no idea what, nitric acid is. I have no idea what potassium oxide is. I don't know what these things are. So I would say of the chapters and what's important, this is one of the more important chapters, at least in the inorganic Gen Chem section. Pull you guys into my computer here. Okay, so chapter 6. So we skipped chapter 5. I'm not even sure what, I think it's on electrons. But we're going to go to chapter 6. We'll be fine without it. So ionic and molecular compounds. All right, so we're going to first talk about ionic compounds and ions. And then we'll move into molecular stuff, which I actually think the molecular is easier. But a while ago, someone had talked about, hey, what happens when we change the number of electrons? Because we've talked about you can't change the number of protons and still be the same material. You can change the number of neutrons and that will give you an isotope, heavier or lighter. We can also change the number of electrons. Now, electrons don't have any mass, so they won't change the mass of your atom, but they will change its charge. So atoms will form a positively charged ion, which is called a cation. I'm sorry, hold on one second. Do you guys hear my French bulldog in the back? He's chasing a fly. It's not the sharpest tool in the shed. Turkey, dude, you gotta go. Go find something else to do. Sorry. So they say like if a cat chases a laser pointer, it's smart. If a dog chases a laser pointer, it's dumb. Well, my French bulldog chases a laser pointer and tries to catch flies, and it's not very bright. It's okay, we love him. So Positively charged ions are going to be known as a cat ion, like a kitty cat ion. And it's important to know that when it's a positively charged, what's happening is it's actually losing an electron. Sometimes we think, oh, well, when we lose something, we're becoming more negative, but the electron itself is a negatively charged subatomic particle. So if we lose it, we're going to become more positive. And then we can also form negatively charged ions, and that's when you gain electrons. And then we form this thing called an ionic bond or an ionic compound when a negatively charged thing sticks to a positively charged thing. So over here are two ions. I've got sodium, but it's written with a little positive in the upper right-hand corner. And then I've got chlorine, which is written with a little negative in the upper right-hand corner. What this is saying is that this sodium, I'm not dealing just with Na. I'm dealing with Na with a plus charge, which means that it has lost one electron. This chlorine is not just regular chlorine, it's chlorine with a negative charge, which means it's gained a single electron. The sun is coming in right there. And what do opposites do? Opposites like to attract, right? So positive and negatives will stick together. So when we're looking at bonds, we have ionic and then we have these things called covalent bonds. So an ionic bond is when you have ions, ionic, where one electron will, or one atom will lose an electron, one atom will gain an electron, and there will be a charge difference that will stick them together. A covalent bond, or sometimes this is called a molecular bond, this occurs when two nonmetals share their electrons. So there's no transfer of electrons, both of them are invested in the bond. Ionic bonds, 99% of the time, are going to be between a metal and a nonmetal. Okay, so it's going to be between something on the left side of your periodic chart and something on the right side of the periodic chart. When you're dealing with a covalent bond, it's going to be two or more things on the right side of the periodic chart. So here's a visual of an ionic bond. I've got M and NM. And M has one valence electron in the outermost shell. It doesn't really like to have just one electron. It wants to have a complete set, or 8. So this electron is actually going to move over here. What ends up happening is now this has a complete set from its lower onion shell, and this has 8 electrons on its outer shell. But by this thing losing an electron, it's formed a positive charge. By this thing gaining an electron, it's formed a negative charge, and now they stick together. In this case over here, where I've got NM and NM, they both have 7 valence electrons. What they're going to do is they're going to share these 2 electrons. Because the goal with bonding is to always work towards getting 8 electrons, or an outer valence of 8. What has 8 valence electrons on our periodic chart? If you remember, it's the noble gases, right? And the noble gases are happy. You don't usually bond with things. I mean, you can force them to, but they're usually pretty content on their own because they have these 8 valence electrons. So everything else is trying to compensate in some way to get to that 8. So in this case, we couldn't transfer the electron, because if this little electron went over here, this guy would be happy with 8, but this guy would only have 6. So instead, they're going to share these 2 or overlap. Now this guy has access to 8 electrons, and then this guy here also has access to 8 electrons. So a little bit different here. These guys are overlapping here with the shared electrons. These guys are just transferring. Metal, non-metal, 2 non-metals. So let's talk about the things that like to lose electrons. So metals in group 1A, 2A, and 3A all readily lose electrons. They will lose electrons until they become like a noble gas, okay? Or they have 8 valence electrons. So above column 1, I don't know if I've told you guys to write this, but above column 1 where hydrogen, lithium, sodium, potassium is, I want you to write a +1. And that's because all of the things in that column form a predictable charge of +1. If I am sitting at lithium and I remove 1 electron, well, then my electron configuration will behave like the thing before it, which is helium, which is a noble gas that's stable. Helium is the only noble gas that's okay with just 2 electrons, okay? That's called a duet. Everything else likes 8 electrons or an octet. Let's look at rubidium, number 37. So rubidium normally has 37 protons and 37 electrons. But rubidium, because it's in column 1, it's going to give up an electron to have 36 electrons, which is going to make its electron configuration like krypton. Krypton is a noble gas, it's stable. So above that first column, you've put +1. Above the second column where magnesium, calcium, strontium are, I want you to put a +2. Those guys, in order to become like a noble gas, they have to take 2 steps back, right? So if I'm magnesium, number 12, in order for me to become like a noble gas, I'm not going to hop forward through aluminum, silicon, phosphorus. That would just be too many electrons to eat up. Instead, I'm going to give away 2 electrons. 1 electron will get me back to sodium. The other electron that I remove will get me back to the configuration of neon, stable. Group 3, which is really like not boron, because boron is on the other side of the zigzag line, but aluminum and gallium, those like to form a 3+ charge. So if you want above that column, put a 3+. Those give up 3 electrons. So if I'm sitting at aluminum, I would give up 3 electrons. I would hop back to magnesium, then sodium, and then neon. So hopefully you have your periodic chart out with you and you're kind of following along. It stops off at neon. It has the electron configuration of the nearest noble gas. So here's the difference between sodium as a regular ground state atom. We've got 11 protons and we have 11 electrons. So this thing is charge neutral and it's got 1 electron floating around in its outermost shell. But that's relatively unstable. So what can happen is that electron will go away and we get sodium with a plus charge. So these 2 things, sodium and sodium with a plus charge, have a different number of electrons. So do note that if I write something like this, oxygen versus oxygen with a 2-, those things are not the same, okay? They're slightly different specifically by how many electrons they have. You'll see here that we've got 11 protons. We have 10 electrons because the outer electron has been removed. And if you look here, here's that 2, 8, 1. What happened to the 1? The 1 disappeared. So the overall size of the atom gets much smaller when it's a cation because that outermost electron isn't taking up any space. So positive really means negative amount of electrons. Positive means you're taking away electrons. Here's magnesium, magnesium in column 2. It's got an electron configuration of 2, 8, and then 2 electrons sitting in the outermost shell. So in order to make an octet or a complete outer shell, I don't want to add 6 electrons. If I added 6 electrons to this, that would make that 8, but that's going to be a lot of work. So instead, I'm just going to remove those. And if I remove those, then I end up with 2 and 8 this here. There's my octet or my complete outer set. You can see it has 12 protons, 12 electrons in the larger magnesium atom. When we go to the magnesium ion, we have 12 protons, but we only have 10 electrons. So I remember somebody had asked, what does it mean when you have electrons like in charged particles and ions? This is what we're talking about with that. We're going to do one more just to really get it down. So if I've got Oh, no, that was it. I guess that was it. Okay. If we were at aluminum, instead of it losing 1 or 2 electrons, aluminum would lose 3 electrons. So if everything lost electrons, then we would just have a universe with like a lot of ions and then a lot of electrons just randomly floating around in space. And that's not what's happening. So something has to counteract that. So the nonmetals on the right side of the periodic chart will gain electrons or eat electrons up, and they will form what's known as an anion. So you may end up hearing me sometimes use the word cation in reference to metals in general. That's because the metals on the left side will always want to give up electrons to form a cation. Negative ions, or our anions, are going to be the things on the right side of the periodic chart. So chlorine over here, traditionally chlorine has 17 protons and 17 electrons. If we look at its electron configuration, it's got 2, 8, and then, oh, what's going on with that outermost electron onion shell? It has 7 electrons. It's so close to being an octet. What can it do? It can steal an electron or take an electron on to get it to 8. So instead of it having 17 electrons and 17 protons, it'll have 18 electrons and 17 protons. Its overall charge will be a -1. So let's just go ahead and do that. Above your fluorine, chlorine, bromine, and iodine column, or your halogens, put a -1, because everything in there likes to gain 1 electron. If you're at fluorine and you gain 1 electron, who are you like electron-wise? Not in your proton definition, but as your electron configuration, you become like neon. If you're bromine and you add an electron, you become like krypton. If you're iodine and you add an electron, you become like xenon. You become like a noble gas. So here are some of the common ions. These guys will always form these charges. So column 1, we've got a +1. Column 2, +2. Column 3, +3. We did column 7. Column 6, which is where oxygen, sulfur sit, put a 2-. Those guys like to give up they like to take on 2 electrons. If we're at oxygen, I can become like neon really quickly if I take 1, 2 electrons. Above nitrogen in the phosphorus column, put 3-. Okay, so nitrogen can take on 3 electrons to become like neon. Phosphorus can take on 3 electrons to become like argon. Carbon and silicon, they don't worry too much about them. They're sort of like plus or minus. They can behave in different ways, so we'll just leave those guys alone. All right, so lithium can become like helium. Sodium becomes like neon. Magnesium can also become like neon. Aluminum can also become like neon. This has to lose 1 electron to get there. This has to lose 2 electrons. This has to lose 3 electrons. Same thing in the other direction, but they have to gain electrons. Fluorine can become like neon by gaining an electron. Oxygen can become like neon. And when I say become like neon, I mean become like neon in the electron configuration sense. Oxygen can do it by 2 electrons, and nitrogen can do it by 3 electrons. So ions are important in regular bodily functions. We need that charged particle in order for it to attract to the outsides of cells and different fluids in the body. Okay, so I want you to write the chemical formula, write the formula and symbol of an ion. So you're going to write the name. You have to figure out what it is. It has 16 protons and it has 18 electrons. Okay, so it shouldn't be too difficult. If I have 16 protons, I'll look at my periodic chart and I know that I'm dealing with sulfur. Okay, so I'm gonna write the symbol for sulfur. I have 18 electrons. So electrons have a negative charge, protons have a positive charge. What's winning out here? The negative is winning out. We have more electrons. By how much? 2. So I'm going to put a 2 minus in the corner here. Yeah, that's it. That's it. You know, and sulfur always forms a 2 minus because that's the column it's in, predictable charge. Okay, so I want you to go through these. So you have the element calcium and the element chlorine. I want you to identify each one as either a metal or a nonmetal. Tell me how many valence electrons each one has. State the number of electrons that must be lost or gained to form an octet, and write the symbol, including its ion charge. When I talk about valence electrons, that is associated with the column number that you're in. If you're in column 6, you'll have 6 valence electrons. Okay, so starting with calcium, calcium is a metal. Calcium is definitely a metal. How am I able to identify that? Just remember, you look at your zigzag line on the periodic chart. Is it to the left of the zigzag or the upper right? If it's to the left, most of the things on the periodic chart are metals. If it's to the right, it's a non-metal. State the number of valence electrons for calcium. So calcium is in column 2, so it should have 2 valence electrons. That means how many electrons are in the outermost shell. State the number of electrons that must be lost or gained in order to acquire an octet. So calcium looks something like this. I'm going to write it with calcium, and then I'm going to put like 2 electrons here on the outside. Is it easier for calcium to lose those 2 electrons or gain 6 electrons? It's much easier for it to lose those 2 electrons. So calcium is going to lose this guy and this guy. If it loses 2 electrons, that means it will end up having a 2+ charge. Okay. Chlorine, on the other hand, is sitting on the non-metal side. So we've got chlorine is a non-metal. It has 7 valence electrons. Don't get valence electrons and charge confused. Valence electrons, how many it has in the outermost shell. It's in, chlorine is in column 7, so it has 7 valence electrons. So if I was to draw chlorine, it would have 1, 2, 3, 4, 5, 6, 7 valence electrons around it, okay? Is it easier to get rid of 7 electrons or to gain 1 electron? It's easier for it to gain 1 electron. If it gains 1 electron, it's going to have a minus charge. Any questions on that, on forming ions? I want you to fill in a couple. So all the guys in the middle, those transition metals, they don't have predictable charges. They can do a variety of things. So if you're looking at like titanium, which is number 22, and you're thinking, what charge does titanium form? You're not going to find it on the periodic chart because it's going to vary. But there are a couple in the middle that do form predictable charges. Go to aluminum. Aluminum is 3+. Okay, go down into the left at a zigzag, zinc. Zinc forms a 2+. And then silver, which is 47, forms a 1+. So it's 3+, 2+, 1+, and a zigzag down and to the left. So you do need to know that zinc and silver have predictable charges as well, even though they're sitting in the transition metals. So we're gonna work on writing chemical formulas for ionic compounds. For instance, like sodium chloride or table salt, I write as NaCl. I don't write it as Na2Cl5. I don't write it as ClNa. There's a specific way that we want to set that up. So ionic compounds will always consist of a metal that has a positive charge and a non-metal that has a negative charge, and they will attract each other, come together, and they always will form a charge neutral molecule, which means that the molecule as a whole has a 0 charge. The positive stuff has to be equal and opposite to the negative stuff. So ionic compounds consist of positive and negative ions. They're formed through ionic bonds, so that difference in charge is what sticks them together. They have high melting points, and they're usually solid at room temperature. So sodium chloride, which is table salt, that is going to take a lot of heat to melt. If you've ever dropped salt on your stove, nothing really happens to it. Again, most of these ionic things will be solid at room temperature. So we've got sodium chloride, which is known as table salt. If we were to magnify it, we would see that there's this lattice structure. So it's like a sodium next to a chlorine, and that chlorine is next to another sodium, which is next to another chlorine, and it creates this 3-dimensional lattice structure. So it's not molecules, but it's a 3-dimensional framework structure. So when writing the chemical formula for sodium chloride, we write it as NaCl. We will write the name of the metal first. You always want to write the name of the metal first, and then the name of the non-metal. And then there will be, if you have more than one of them, you will write a subscript. So in this case, we don't. We just have one sodium sticking to one chlorine. And so my subscripts are just an inferred one. You don't have to write in one. The important thing is the total positive charge has to equal the total negative charge. So if sodium has a +1 charge and chlorine has a -1 charge, one sodium is able to balance out one chlorine, right? Or a +1 and a -1 gives us 0. This one is easy to do because it's 1 and a 1. So they're sort of perfectly balanced for each other as is. When the charges are different, it's a little more complicated, but there's a pretty simple way to figure it out. So when we're looking at magnesium, for instance, magnesium likes to lose 2 electrons. Chlorine likes to gain 1 electron. So in order to get rid of both of these electrons, I'm going to need 2 chlorines, right? 1 electron will go to one chlorine, the other electron will go to the other chlorine. So in this case, I'll get Mg with a 2+ and a chlorine with a minus and a chlorine with a minus that sticks together. The charge here is a 2+, and I have only one of them. The charge here is a -1, but I have 2 of them, which gives us a 2- for a total 0. So my formula becomes MgCl2. So hopefully you get that conceptually. I'll show you another one here. So I have sodium. Sodium has 1 valence electron or likes to form a +1 charge. Sulfur has 6 valence electrons or likes to form a 2- charge. So we need an electron from one that would bring it to 7, but then we need an electron from another to bring it to an octet or 8. So 2 sodiums for every 1 sulfur. Now, the fastest way to do this is not to write all these pictures out with their little electrons. It's to do the flip-flop rule. Okay, so I'm gonna go back to the last slide. Here I've got magnesium and chlorine. So the fastest way to figure out how many magnesiums and chlorine I need, don't draw all this out. What I want you to do is write the symbol for the metal, magnesium, with its charge, okay? So magnesium is in column 2. It always likes to form a 2+ charge. Chlorine, I'm gonna write it over here somewhere. I haven't combined them yet. Chlorine always forms a -1 charge. Now what we're going to do is we're gonna take the magnitude of each charge, not the positive or the negative. We're gonna kind of ignore the positive, negative. We're just gonna take the magnitude of it. That becomes the subscript of the opposite guy. So in this case, magnesium, how many do I have? I have 1. Chlorine, how many do I have? I have 2. The 2 drops down here. The 1 drops down here. That will get you charge neutral every time, okay? Let's do it for the next slide and then we'll do a bunch of practice. In this case, again, you could draw all this stuff out to try and come up with it, or we can just flip-flop. So in order to flip-flop, write the symbol of the metal with its predictable charge. So sodium always forms a +1 charge. Sulfur, hello. Sulfur always forms a 2- charge. Circle, circle. This is gonna drop down to here. This is gonna drop down to here, or I'm gonna have 2 sodiums to balance out every 1 sulfur. This goes there. This goes there, and that is in fact what we have here, right? 2 sodiums for 1 sulfur. So I would recommend just flip-flopping. So try it out here. Write the ionic formula of a compound that is formed between barium and chlorine. And specifically, it gives you barium 2+ charge. If it didn't give you the 2+, you could look at your periodic chart and say, oh, well, barium's in column 2, so it has a 2+. And chlorine, which is in column 7, so it has a -1 charge. So flip-flop those and come up with your formula. All right, so barium. So I'm going to write my metal, barium. Barium, come on now, buddy. Barium with a 2+, chlorine with a - charge. As you get better at this, you don't necessarily have to write it out. Like I can just sort of know, I know what the formula is because I know how to flip-flop, but in the beginning, write it out. So this 2 is going to drop to the chlorine. The inferred 1 there is going to drop to the barium. So there should be 1 barium for every 2 chlorines. We can go back and check to make sure it's right. So barium has a 2+ charge, and I have how many in this formula? In this formula, I have 1. Chlorine has a -1 charge, and how many of them do I have? I have 2 in this case. All right, so 2+ and a 2-, 0. We are charge neutral. You don't have to check them every time. As long as you're flip-flopping correctly, you will get to a charge neutral molecule. So any questions before we do practice, but any questions on where these 2s are getting put and 1s are getting put? The one thing I do see happen a lot is people will take this and they'll drop it down to the barium in the 1 and they'll drop down to the chlorine. You can't do that. You don't want to have barium to chlorine 1. You need to take the 2 and bring it over to the other guy. Okay, let's just do some practice then. So I want you to try and come up with the correct formula for each of these. We've got sodium and oxygen, aluminum and chlorine, and magnesium and nitrogen. And this one's really nice. It gives you the charges as well. You don't even have to look them up on the chart. Okay. So the way that the slides are set up, they guide you into how to answer them. So it says, hey, these are ionic compounds. On a test, it might not explicitly tell you it's an ionic compound. So you first want to identify, is this a metal and a non-metal? Because if it's not, you use a different technique that we haven't talked about yet. So in fact, all of these are containing a metal with a non-metal. So we will be flip-flopping. There's a 1 here, an inferred 1 here, 2 here. So flip-flop, I should have 2 sodiums for every 1 oxygen. The 2 here is coming from the charge magnitude there. The 1 there is coming from the charge magnitude on that. Aluminum, so what did we say? This one. Al3 and Cl, so that means I need 3 chlorines and 1 aluminum. The 3 gets dropped down there, the 1 gets dropped down there. Mg2 and N3, so I need 3 magnesiums for every 2 nitrogens. The 2 is getting dropped down to the nitrogen, the 3 is getting dropped down to the magnesium. Okay, I'm gonna give you a couple more. I'm not gonna be quite as nice and give you the charges though. Okay, I want you to combine zinc and nitrogen, magnesium, and sulfur. Aluminum, and oxygen, and cobalt, and chlorine. Okay. Okay, let's come back together. So zinc and nitrogen. So zinc is one of those transition metals you do need to know that has a predictable charge. So zinc is always a 2+ charge. Nitrogen is always going to form a 3-. So we flip flop. So you should end up with Zn3 and 2. Magnesium and sulfur. So magnesium is a 2+. Sulfur is a 2-. So I'm going to flip flop here. I get Mg2S2. Now this is an important thing. With ionic compounds, if you have a 2 and a 2 or a 3 and a 3, anything like that, you can reduce down. Okay, so we will reduce this down to Mgs. One of these for every one of those. Only with ionics. Aluminum and oxygen. Aluminum is a 3+. Oxygen is a 2-. Flip flop. We end up with Al2O3. This last one here was just to mess with you a little bit. Okay, cobalt. So we have cobalt. What is its charge? You go to the periodic chart and you go, I don't know. We know what chlorine's charge, it's -1, but we don't know cobalt's charge. So we can't come up with the correct formula. In this here, there is not enough information given to you. We have to actually add a Roman numeral in here that lets us know what the charge is. And we'll talk about that in a minute. We'll get into that, but the way that it was written before, just saying cobalt and chlorine, I couldn't combine them together in any sort of way. All right, so now that we know how to write these formulas, we want to name them as well. So iodized salt contains Ki, which is potassium iodide, to prevent iodine deficiency. All right. How do we name these things? Everything from that previous practice. Well, you're always going to name the metal first. So we don't call it chlorine sodium or chlorine sodiide. We would call it sodium. And then we take the first syllable of the nonmetal, we cut it off and we put IDE at the end of it. So I don't call it sodium chlorine. I call it sodium chloride. On that previous slide here, I don't call it potassium iodine. I call it potassium iodide. Okay, so when you see the IDE, it's referring to the element. Put a space between the metal and the nonmetal. So looking at some examples that they have here, here's potassium and iodine. It's made up of potassium and iodine. We IDE the second guy, so it becomes potassium iodide. Magnesium and bromine. Magnesium, we truncate the last guy and we ide him, so it becomes bromide. And then we put them together, magnesium bromide. This thing here is aluminum oxide. We cut quite a bit off of oxygen, okay? We don't bring the Y or the G, we just keep the O and the X. And that's it. I mean, it's not that bad, okay? It gets a little bit more complicated when we have a metal that doesn't have a predictable charge. But for now, as far as metals and nonmetals that both have predictable charges, that's all you do. So identify the cation and the anion if we're following the steps. Name the cation by its elemental name. Name the anion by first using its first syllable and then IDEing the end. And then you just stick them together. So this thing here, I want you to try and name that. K2O. So with K2O, we have the first thing is potassium. The second thing is oxygen. We need to truncate the second guy and IDE him. So this should be just potassium oxide. There are 2 potassiums in this one. You don't have to worry about taking that into account as long as they're both predictable metals. Potassium oxide will give us enough information to get back to this formula. So if you were to just give me this thing here, potassium oxide, and I was to go backwards to write the formula, potassium always forms a +1, oxygen always forms a 2-, flip-flop, K2O. It was more than enough information to get back to this thing. Okay, so go ahead and name the following 3 compounds here. Okay, so first one here is calcium and oxygen. So it is a metal. It does have a predictable charge. So we can use our system by saying calcium oxide. Next one, we've got aluminum and oxygen. Again, it's a metal and a non-metal, predictable charge on the metal. So we can call this aluminum oxide. Last one, magnesium and chlorine. Metal, non-metal, metal has a predictable charge. So we call this magnesium chloride. There we go, calcium oxide, aluminum oxide, magnesium chloride. All right, so go ahead and in this matrix, write all the different combinations of these. So for this, for instance, in this first one, you've got sodium, you're combining it with bromine. Then we're gonna combine sodium with sulfur and then sodium with N3-, and then the same thing with the aluminums. I'll give you 2 minutes. The drawing will probably take you the longest part. All right, so this first guy over here in the corner, we have sodium and bromine. They both have a 1-to-1 charge, so it's just going to be NaBr. And the name for this is sodium bromide. I'd the second guy. Over here, we've got sodium and sulfur. Sulfur has a 2 charge, so the 2 needs to get dropped to the sodium, Na2S. And we call this sodium sulfide. Last one here, we've got Na plus 1. This one, nitrogen has a 3-, so we'll put a 3 there. Nitrogen will have the 1 from the sodium. And we end up with sodium nitride. Here we've got aluminum and bromine, so flip-flop, and we will end up with AlBr3, aluminum bromide. Here, flip-flop, we'll end up with Al2 from the sulfur, S3 from the aluminum, aluminum sulfide. And last one here, flip-flop, we get a 3 and a 3, so those we can reduce down. So it should be Aln, which would be aluminum nitride. Any questions on that? That sort of encompasses everything from this very first part. And understand how to do that, you've got the first thing check done. So now let's get into what happens when you have a metal with a varying charge. So all those things in the middle, minus zinc and silver and like cadmium as well. Sometimes scantium too will have a predictable, they'll classify it as predictable charge. But what you have to do is put a Roman numeral right after the element to tell me what charge you're working with. So if you're dealing with copper with a 2+ charge, you have to tell me it's copper with a Roman numeral 2 next to it. If it's copper with a 1+ charge, you have to write copper Roman numeral 1. Iron here, we've got a 2+ and a 3+. So again, you have to identify that you're using either the 2 charge or the 3 charge. This is not, and this happens all the time, this number is not telling you how many coppers you have or how many irons you have. It is telling you the charge. Charge, charge, charge. So when I say chromium 3, I'm not saying I have 3 chromiums. I'm saying I'm dealing with chromium with, in fact, a 3+ charge. You don't have to have these all memorized, okay? You will always be able to figure out what the charge is. So like here's a bunch of different metals in there, different predictable charges. Bismuth likes to form a 3+ and a 5+. Chromium likes to do 2 and 3. Cobalt likes 2 and 3 as well. Copper likes 1 and 2. You don't have to have all these memorized, but you do need to see how this correlates to the Roman numeral. So looking at this thing here, MnF2, I'm gonna write this on my dry erase board. MnF2. So if I'm going to name this thing, I'm going to follow a very similar system to what we did before. We're going to name the metal first. This is manganese. This is not magnesium, okay? Not Mg, it's Mn, manganese. Now, when I find manganese on the periodic chart, it's number 25. It's sitting in the middle with the transition metals. So I know I need a Roman numeral. So I'm just going to put a parenthesis set in there and I'll come back to it. So I've got manganese with some sort of charge. And then the second thing is fluorine, which I eyed. So fluoride, fluoride. So now I need to go back and figure out what is my charge on manganese. Well, what do you remember about your ionic compounds? They have to equal a 0 charge. So what you're going to do is go from what you do know to get the charge of what you don't know. What is the charge on fluorine always? Fluorine always has a -1 charge, correct? Because it's in column 7. But how many of them do you have? You have 2 of them, so I need to multiply that by a factor of 2. So my negative charge is -2. I'm gonna put like a little line between these. So if this is -2, manganese in this case has to be a +2. There's no other option because what's over here has to be equal and opposite to what's over here. So this would be manganese 2 fluoride. You can always go back and check to make sure you've done it correctly by writing it out and seeing if you get the same formula. So if I'm dealing with manganese 2, I'm going to write my symbol Mn. This is telling me the charge. Fluorine always has a -1 charge, flip-flop. I get MnF2. Awesome. That is, in fact, the same thing. We did that correctly. Any questions on that outside of, obviously, we just want to be able to practice it a bunch? Where those numbers are coming from, why does it have to equal 0? Yes, no. Let's do some more of them. See if the slides have any, and then I can give you some practice. This is just showing you some of the varying charges. Again, you don't need to have those memorized. So determine the charge of the cation from the anion, or figure out what you don't know from what you do know. Name the cation, and then use a Roman numeral to tell you what the charge is. Add the anion and stick them together. So if I've got this thing right here, FeCl2. So FeCl2. So this is iron. When I look at my periodic chart, iron has an unpredictable charge, so I'm going to throw a Roman numeral there. And then this is chlorine, which becomes chloride. Iron, something, chloride. So I have to figure out the charge of iron. Okay, well, chlorine always has a -1 charge, and there's 2 of them. So this is -2. So iron in this case has to be +2. Iron 2 chloride. This is very similar to the one we did before, right? We had something in column 7, 2 of them to balance it out. Let's do a couple more. Okay, FeO, Fe2O, FeO2. This is a group of compounds called iron oxides because they all contain iron and oxygen, but they each will be slightly different. So I want you to try and tell me what the charge is for each of those irons. right, so I'm going to go over these just so that we can get out on time. So each one of these is an iron oxide. It's iron combined with oxygen. So I'm going to write iron, I'm going to put a parentheses, and I'm going to put oxide for every single one because it's a family of iron oxides. All right, and iron oxide. Now the difference here is what the charge is on the iron. So in this case, and I can put a little squiggly line or something between. So this whole thing has to equal 0. Oxygen is always a 2- charge. In this case, I only have one of them. So it's just 2-. So iron has to be a 2+ charge to balance that out. So this is going to be iron 2 oxide. Over here, I'm going to put a squiggle line. Oxygen, 2-. How many of them do I have? Just one. So it's a 2- charge. So this has to be a 2+ charge. But look at what's going on. There are 2 irons that will in total create a 2+ charge. So each of the irons has a +1 charge. Here's a plus. Oh, it should look like a +1. Iron with a +1 charge, and then iron with a +1 charge. Here's 1, here's 2 to give us overall 2+. So each one has a charge of 1. Or if you're going from here up, you multiply the subscript. If you're going from here down, you divide by the subscript. Okay. If you want to go back and recheck, okay, if this is iron with a 1+ charge, +1, and oxygen has a 2- charge, flip-flop, we end up with Fe2O. And it is, in fact, the same one. This is probably the most complicated. When you have 2 of them, you just got to make sure you divide, or if you have 3 of them, you divide. This last one here, we put a little squiggle line through it. Oxygen is a 2- charge. How many of them do I have? I have 2 of them, right? So I've got to multiply it by 2. So this is an overall 4- charge. So this has to be a 4+ charge. I'm not dividing it through any, I just have 1 iron. So this will be iron 4 oxide. First guy's iron 2 oxide, second one's iron 1 oxide, third one is iron 4 oxide. So it's not enough when you are writing a formula name to just say iron oxide. You say iron oxide, I have no idea what formula you're talking about. Okay, there's a bunch of different options. You've got to include the Roman numeral in there with, you know, whatever the charge happens to be. Questions, things you don't like that feel shaky, that you want to do some more problems on. Next time, I'm guessing this is probably an area where people want to do a little bit more work. We'll do some more practice with that. Okay. Then we'll leave it at that for today. Next week we'll get, or next time we'll get into polyatomic ions. Yeah. If you have any questions, stay around. If you don't have any questions, just go ahead and log off so that I know who does have questions. Otherwise, I will see you all on Wednesday. Feel free to email me. We can chat about labs and what have you if need be. All right. Bye-bye, guys. Bye, Abigail. All right, Deborah, I'm going to put you in a waiting room for a second, and I'll bring you back in. Kaylee, you there?